Hello and welcome to Uncertainty in Measurement. You know that science is all based on measurement, and we can't have a measurement without uncertainty, so learning uncertainty is a must. Before I start, if you are new in this channel, don't forget to subscribe and push the bell button to see more videos. Okay, let's start. I have a vessel of water and I'm gonna have a measurement on temperature. For measuring the temperature, I need an apparatus. A simple mercury thermometer could be the best one for the present time for me. Okay, I put that and then I watch it to see the mercury level is stabilized and then I do my measurement. My scientific report must be something like this. 45.6, which is named the value, and 0.1 plus or minus, which is named uncertainty. Okay, today you will learn how the uncertainty is found. Basically, uncertainty is coming from errors. We have different types of errors: systematic errors and random errors. Let's learn them one by one. First, systematic errors. Systematic errors are the errors coming from the apparatus. For example, because of the faulty apparatus I use, it may have low quality and something like that. Or maybe from the zero error. The zero setting of apparatus can drift due to usage, so that it no longer reads zero when it should. This is called zero error. Okay, anyway, if the systematic error is small, I can say that the measurement is accurate. Pay attention, accuracy is related to the systematic errors. The smaller the systematic error, the more accurate the measurement you have. Okay. On the other hand, I have random errors. Random errors are coming from improper measurement or maybe from the fluctuations in the quantity. Anyway, you know that, for example, the temperature of the water in this vessel may not be homogeneously the same everywhere. So may I put a thermometer in other parts of the water and see different temperatures. Anyway, these fluctuations and maybe personal faults may make some random errors. So random errors originally are from the experimenter and the condition of the experiment, which is named the measurement. Okay, anyway, if they are small, we can say that the measurement is precise. Pay attention, precision is related to random errors, to the experimenter and the condition of the experiment. It is not at all related to the apparatus. Accuracy is something related to the apparatus. Okay, let's continue. Look at this. Here I have a short-sighted person who is looking at an adjusted clock. The clock is okay and it's measuring the time in proper way. There is no problem with the clock, but the person is not a proper person for that. Anyway, he is a short-sighted man and cannot see that clock easily. Anyway, this measurement is accurate. Why? Because the apparatus is okay. There is no problem with my apparatus. But is it precise? No, it is not. Why? Because the experimenter has not good condition. Look at this one. I'm driving a car. I have no problem in my vision, so basically no visual problem as an experimenter, but unfortunately the GPS of my car is not properly connected to satellite, so it cannot measure the distance or measure, for example, the time for my destination and so forth. So it's not reliable anyway. Is this measurement accurate? No, it's not accurate because the apparatus anyway has some problem. But it is precise because I have no problem. As an experimenter, I can do the measurement easily with no problem. Okay, hope you got it. Let's continue. I'm summarizing. Errors could be systematic, originated in apparatus, and how can we reduce them? First, We can recalibrate the apparatus if possible. If the quality of the apparatus is not really bad, we can recalibrate it if possible to decrease the systematic error. The second thing I can do is using another apparatus to compare the results. But we have random errors originated in measurement process, basically related to the experimenter and the condition of the experiment, fluctuations and so forth. Number one, how to reduce that? Number one could be using the apparatus in proper way. Anyway, we should be skillful enough to do that. And number two is repeating readings and taking the average. Okay, suppose that this vertical axis is indicating the degree of uncertainty I may have. How should I make a measurement with smaller uncertainty, which is my favorite? First, I should be a skillful person. Suppose that I do the measurement with smaller and the smallest even personal faults. So it's the best thing I can do for the first step. Okay, I am a skillful person. I do my measurement with the least personal faults, but what should I do more? Anyway, I should do a measurement. For a single measurement with less accurate apparatus, I have a degree of uncertainty. What should I do more to decrease the uncertainty? I should reduce, I think, the systematic errors. So I should work on the system. I think I should do the measurement and this time with more accurate one. So if I do the single measurement but with more accurate apparatus, anyway the uncertainty will be decreased. So another step will be using more accurate apparatus to decrease the systematic error. What should I do for less random errors? For the first time, for decreasing the random errors, I did the measurement in a skillful way. The other thing I can do is that instead of single measurement, I do repeated measurements with more accurate apparatus. In this time, rather than systematic errors, also repeated measurements will decrease my random errors. So I will have smaller uncertainty. Now is the time to go back to the accuracy again. How to find the accuracy? Accuracy is all related to the device, to the measuring device, to the apparatus. For example, if the apparatus is a simple ruler like this, 1 centimeter between 24 and 25 has been divided into 5 equal parts. The minimum value I can measure by using this apparatus is 1/5 of a centimeter or 0.2 centimeters. That's all. It's named accuracy. So the accuracy is the minimum value, the minimum graduation, and the measuring device. Let's look at the other one. This is a simple ruler also with a different graduation. Here between 33 and 34 has been divided into 10 equal parts. So the minimum value I can measure by using this apparatus is 1 millimeter or 0.1 centimeter. This is an analog apparatus. Why analog? Because there is no digital screen on it. Another analog apparatus could be this kind of voltmeter with a hand. As you see on the screen, the range of this voltmeter is between 0 and 10, and the minimum value you can measure by using this apparatus is 1 volt. Accuracy is 1 volt. What about the digital apparatus? Digital apparatus will have a digital screen. For example, here I read 33.3. The last right digit will have the more sensitivity to change. If you make any mistake or any change on your measurement, the last right digit is the first digit which undergoes a change. So here the number place is very important. The last right digit in this apparatus has the number place of tenths. The number place will be the accuracy. So accuracy will be 0.1 volt. Now it's the time to learn the uncertainty. Uncertainty will have two different methods. Uncertainty in single measurement and uncertainty in repeated measurements. So let's learn them one by one. Anyway, for a single measurement, you may use an analog or a digital apparatus. First, you should specify the accuracy. And the rule is this: for finding the uncertainty on analog apparatus, you should divide the accuracy by 2. Uncertainty will be plus or minus a half of the accuracy. On digital apparatus, the uncertainty is easily plus or minus the same as the accuracy. So first, you should specify the accuracy, and then on digital one, the same. On analog one, half of the accuracy will be your uncertainty. Let's learn more in some examples. This is a digital ammeter, and I read 1.26 on the screen. The last right digit is something I will specify the accuracy by using the number place. Number place of this 6 is 100th, so it's 100th of an amp. I think the accuracy is 100th of an amp. So uncertainty will be plus or minus the same value, plus or minus 0.01 amp. Why? Because it's digital. The same as the accuracy with the plus and minus will give me the uncertainty. What should I do with analog one? Okay, you already learned the minimum graduation on this type of ruler, for example, will be 0.2 centimeter as the accuracy. As this is analog, you should divide it by 2. So you will get the uncertainty as plus or minus 0.1 centimeter or 1 millimeter. The other one will have the minimum graduation of 1 millimeter or 0.1 centimeter as the accuracy. As this is analog, I should divide it by 2. So I will get plus or minus 0.05 centimeter or half of a millimeter as the uncertainty. Look at the last ruler. How should I find a real value by using this apparatus? Okay, it's very easy. As the uncertainty is half of a millimeter, for example, I put a wooden block like this here, and I try to find a scientific report, a scientific measurement. Okay, here I see 10 millimeters, 20 millimeters, and 4 millimeters. So totally 24, but it's a little bit more than 24. It may be 24.3, 24.2, something like that. And then I put the uncertainty at the end. So it's 24.2. It's the last right digit is 2, is something I guess. It's not that important. Plus or minus 0.5 as the uncertainty I have already found. So I should remind you something very important. Look at the last right digits. They must be in agreement. Otherwise, the report is not acceptable. Look at this example. Regarding the analog thermometer in figure, express the temperature of the room and its uncertainty. First, let's find the uncertainty, and before that, the accuracy. Here between 0 and 10 has been divided into 10 equal parts. So I think the accuracy will be 1 degree Celsius. I divide it by 2 as it's analog one. So uncertainty will be plus or minus half of a degree. At last, the value. The value is 25. It's almost 25. So I can write it 25.0 plus or minus 0.5 degrees Celsius. But the question is that, is it really necessary to put a 0 after this decimal point? Yes. This 0 has the number place of tenths. It must be in agreement with the number place of tenths for the uncertainty. Otherwise, it's not accepted. It's very important. Now, I have a very important warning for you. What the warning is. Look at these two voltmeters. The left one is digital and the right one is analog. On the digital screen, I read 385. So I can write the voltage is 385 volts. And you see that even the last right digit, the 5, which is in the number place of ones, is the digit I read on the screen. I do not guess it. But on the right side, in an analog screen, I can report the value as 385, but 8 is the last digit I read. 5 is something I guess. I'm not sure about this 5, so I guess it. So it's a big difference between the two values. The last right digit in analog apparatus is something you guess, but in digital voltmeter is something you read. They are totally different. In general, if the reported value is V equals 385 volts, it's not easy to determine the uncertainty. You should know about the nature of the apparatus. If the apparatus is digital voltmeter, okay, you can say the last right digit is 5, the last right digit I read and I can rely on. 5 has the number place of ones, so the accuracy is 1 volt and the uncertainty will be plus or minus 1 volt as it's digital. What about the analog one? If I use analog voltmeter, 8 is the last number I read, so I should rely on the number place of 8. The number place is tens, so the accuracy is 10 volt or 10 volts, and then I divide it by 2, I should get 5, yeah, plus or minus 5 volts. It's different. As you see, the nature of the apparatus will totally change the uncertainty I should report. Another example could be this one. Suppose that the temperature has been reported like 36.2 degrees Celsius. Let's find the last figure you read, the accuracy and the uncertainty. If you use analog thermometer, the last digit you read will be 6, not 2. You know why? Because 2 is something you guess. So 6 has the number place of ones, the accuracy is 1 degree Celsius, and the uncertainty will be half of that as it's analog. So it's half of a degree. If I use digital thermometer, the situation is different. I know that also the 2 is the digit I read. So the number place of that is 1/10. So the accuracy is 1/10 of a degree, and then I should report it as the uncertainty plus or minus 1/10 of degree. Another example. A measurement of temperature of a room has been done with a digital thermometer to the result of 36.8 degrees Celsius. How should we express this result? Okay, the last right digit, 8, is something I read on the screen. So the number place of this 8 is 1/10, so the accuracy is 1/10 of a degree. Plus or minus the same value will be the uncertainty. So the reported value will be 36.8 plus or minus 0.1 degrees Celsius. Look at this one. It's a multiple choice question. The diagram shows the temperature of a liquid before and after heating. What is the best estimate for the temperature increase of the liquid? Temperature increase. Okay, first let's check the accuracy to find the uncertainty. Between 25 and 30 has been divided into 5 equal parts, so accuracy will be 1 degree. And I divide it by 2 as it's analog, so uncertainty will be half of a degree. So option A. But let's find the value also. Here I have 65, 66, 67, 68. It's 68. A little bit more. Forget about a little bit more. Here also I have 24, and if I subtract the 2, it will be 44. But please don't forget 44.0, because the uncertainty has the last digit in the number place of tenths. So also 44 must have the same number place at the end. Otherwise, it's not accepted. So I opt for A. Now the last step, how to find the uncertainty in repeated measurements. I told you repeated measurements is the best method for reducing the effect of random errors. Suppose that I do the measurement but not just once. In the first measurement I get 1.17, then I continue to more and more values. In 5 measurements I have got these values. For finding the accepted value, I take the average. Average is 1.158, but I do not rely on calculator. Physically, I know that 8 is not accepted here. The last right digit here is in the number place of thousandth. It is not accepted because all the values, the measured values on the last right digit have the number place of hundreds. So I should round it up. 8 is greater than 5, so it's rounded up. I should add 1 to 5 and write it 1.16. It's the accepted value. The next step is finding the uncertainty. Uncertainty as a rule is half of the range. What the range is the maximum value minus the minimum value, and then I divide it by 2 to find the uncertainty. Let's substitute 1.19 and 1.12 for max and mean, and then take and divide them by 2 to find the uncertainty. Here uncertainty mathematically is 0.035, but I do not accept this one because the last right digit also is in the number place of thousandths, but the given value in max and mean are in the number place of hundredths, so I should round it up again. I can do it like that. So I write 0.04, I rounded up the value as the uncertainty. As you see, 6, the last right digit of the value, and 4, the last right digit in the uncertainty, are in agreement. They are both in number place of hundredths. Look at this example. Repeated measurements of temperature of a room have been done with a digital thermometer to the results of 24, 23, 25, 26, and 25 degrees Celsius. How can we express the temperature? Okay. As it is a set of repeated readings, so I should first find the average. I add them up and then divide them by the number of measurements, 5 measurements, so I divide them by 5, and I get 24.6. Look at this value. Mathematically it's accepted, but physically no, because the last right digit is in the number place of tenth, but all the given values at the last right digit are in number place of ones. Based on the rules I have already taught in operations, it's not accepted. So I should do something to round them to be in agreement with the given values. 24.6 is rounded up. As 6 is greater than 5, I should add 1 to 4 and write it as 25, rounding up. If it was 24.3, I could write just 24. Anyway, it's 25 now. This is the accepted average. What should I do next? It's very easy. I should go for the range, and half of the range will be my uncertainty. Range is 26, the maximum value among the given values, the measured values, and the 23 as the minimum. The range is 3. I should divide it by 2 and find 1.5. 1.5 mathematically is correct, but physically no. Why? Because as you see, the last right digit again here, the last right digit is 5 and it's in number place of tenths. But the last right digit in the given values in the max and mean are in the number place of ones. So again, I should round it. As 5 and greater than 5 are rounded up, I should round it up to get 2. So the accepted value in my report will be 25 plus or minus 2. This is the last part of this lecture. I hope you enjoyed. Don't forget to subscribe and push the bell icon to see more videos. See you in next videos.